Baran.
Good morning, Sujata ma'am. Good morning, everyone. Kyle? Okay, thank you, Kyle. Manik, you can start the session. Thank you.
Yes, ma'am. Ma'am, am I audible?
Yes, you are.
A very good morning to one and all, and welcome to the day 2 of our workshop, Know Your Molecules by Sophisticated Technique of by TGA, SEMTEM, XRD, GCMS, and LCMS. Organized by Chemistry Department of St. Xavier's Autonomous College, sponsored by RUSA. So, just like yesterday's fruitful and overwhelming session, today we will know more about the molecules with sophisticated technique like XRD, GCMS, and LCMS. Before we start with the session, I would like to give some technical instructions for the smooth conduction of workshop. Dear participants, please keep your audio off throughout this session. Type down your queries at the end of the session in the Zoom chat box or in the comment section of YouTube. Your queries will be addressed at the end of the session. Participants need to attend all 2 sessions and need to fill the feedback forms in order to receive your e-certificates. Our first session is to know about the structure and the nature of our molecule using sophisticated technique of XRD. On the behalf of my chemistry department, I am pleased to invite our first speaker, Dr. Sujata Kashyap, who will introduce us to the technique and enrich us and enlighten us with her knowledge and experience in the field of single crystal XRD and supramolecular chemistry. Dr. Kashyap is currently working as a scientist in Environmental Hydrology Division, NIH, Roorkee. Dr. Sujata Kashyap has done her PhD from IIT Roorkee. And talking about her colossal contribution in the field of research, she has about 17 research papers published in well-reputed national and international journals. She has also received various CSIR fellowship and has been part of a number of national and international conferences. And apart from her contribution in research, Dr. Kashyap has also had teaching experience for UG and PG students. Ma'am, we are immensely delighted to have you here, and I'm sure all participants will be greatly benefited from your session. Thank you.
A very good morning to all of you. Am I audible?
Yes, ma'am.
Yes, ma'am.
Okay. So a very good morning to all of you. I'm Dr. Sujata, and I'm working as a consultant in a pharma company that is Exa Parenteral Limited, Roorkee. So I'm working as a consultant in Exa Parenteral Limited, Roorkee. And first of all, I would like to thank the organizer, especially Dr. Abhilasha Jain, for giving me this opportunity to interact with all of you on the topic basic fundamentals of X-ray and its application in powder as well as in single crystal XRD. So what is XRD? XRD is X-ray diffraction technique. So as the term itself suggests that it is composed of two words, X-ray plus diffraction. So we'll study X-ray and then diffraction and how the combination of these two make a technique and through which we can identify our molecule. So what is X-ray? X-ray is nothing, just it's electromagnetic radiation. So when we when we arrange the radiation either in increasing or decreasing energy, then we get a series, and that series is known as electromagnetic spectrum. The X-ray falls in between ultraviolet and gamma rays with a radiation with a frequency of 10 raised to the power 16 to 10 raised to the power 20 hertz. It's a high energy radiation, and therefore the wavelength is a very low, and the wavelength lies in a range of 1 to 100 Armstrong. There are two types of radiations, ionizing radiation and non-ionizing radiation. So X-ray belongs to ionizing category, and it has a very beautiful property that it has very strong penetration power. Therefore, the X-ray can penetrate through the tissue of the body, but it cannot penetrate through the bones. So it gives the illustration on an X-ray plate about the fractured bone, which is very helpful for the doctors. And since it is an ionizing radiation, therefore long-term exposure of X-ray is very harmful and very dangerous. And therefore it is always suggested, and it is also been in practice, that those persons or operator who are working with the X-ray must wear a badge, that this kind of radiation monitoring badge, which measure and counts the amount of radiation, how much radiation they have been exposed of. So comes how we know about what is X-ray now, how it is generated. So X-ray is generated in a cathode ray tube, in which this is the filament. We heat the filament, and because of the heating, the electrons is being ejected. Then a high electric potential is applied. A high electric potential is applied between the filament and the target material. And because of this applied electric potential, these ejected electrons get accelerated. And when these accelerated electrons hit the target material, X-ray is produced. In the process of production of X-ray, enormous amount of energy is released, and because of that energy or heat, the temperature of the target material get increased. So to cool down the temperature, there is a water jacket. You can see there is a water jacket, and in this water jacket, there is a continuous supply of water, which reduces the temperature of the target material. Generally, the target material used are copper, nickel, molybdenum, and tungsten, etc. Next come the spectra of X-ray. When we see the spectra of any radiation, we see many peaks. Similar to that of other radiations, if we see the spectra of X-ray, then we find two types of peak. There is a continuous peak, you can see. There is a continuous peak, and there is a characteristics line peaks. So the continuous spectra is known as Bremsstrahlung spectra or white radiation, whereas the line spectra is known as characteristic radiation. Why there is two kind of peaks we can see in the spectra of the X-ray. So first, when the thermoionic electron accelerated thermoionic electron hits the target material, a white continuous spectra, or there is an emission of white continuous spectra radiation, and that is called white radiation or Bremsstrahlung radiation. This white radiation is believed, why this white radiation is produced, it is believed then when these accelerated electron hits the nuclei of the target material. This electron hits the nuclei of the target material, the Bremsstrahlung or continuous or white radiation occurs. If we see, when the kinetic energy held by this electron is completely converted into the all X-ray, like all the energy which is being carried by this electron is totally converted into the radiation, then in that case, E max, maximum energy, will be equal to h nu with the maximum frequency, or hc by lambda, that means minimum wavelength. In this condition, that is the maximum energy or the minimum wavelength is called as Dawn-Hunt limit. Now we study that why there is a white radiation or continuous. Now we have to learn why there is a characteristic peak occur. So when the energy of these accelerated electrons is more than that of the threshold energy or excitation potential of the electrons of the target material, then a discrete peak along with the white radiation also appears in the spectrum. This process, the line spectra occurs in a two-step process. In first step, what happens when this electron hits the target material, it knock out one of the electron from the lower energy level. And in second step, the electron from the upper or higher energy level jumps down to fill the vacant hole here. And during this process, like from electron coming from upper energy level to or higher energy level to lower energy level, there is a production of a radiation or emission of a radiation, and because of this, a line spectra generates in the spectrum of the X-ray. The energy of this radiation is equal to the difference between the two energy levels. And this energy or the energy of this peak is characteristic or specific for each specific material. For molybdenum, it will be specific. For copper, it will be other specific. And therefore, it is also called as characteristic peak, because a specific target material have the specific characteristics peak energy. Then whenever the X-ray interacts with any matter or material, there are many phenomena can take place. It could be emission, absorption, or diffraction. So we human beings are very intelligent. We always thinking how we can use any of the phenomena, and like how we can use those phenomena for making techniques and utilize those techniques for identifying our molecule. So similarly here, when X-ray interacts with any material, the phenomena could be emission, absorption, or diffraction. So based on the emission phenomena, the technique develops is the direct method or XRF, that is SEM-EDX or XRF. And these two techniques are used for elemental analysis and for surface morphology, as we already discussed previously yesterday. Now, with the help of diffraction, the technique is developed single crystal XRD and powder XRD. What is diffraction? Whenever X-ray falls on any material, it gets scattered in all possible directions. But when the same X-ray falls on a crystalline material, then the scattered ray, they themselves reinforce each other to be aligned in one particular direction. That is the difference between how we can select whether we'll go for XRD or not. Like whenever radiation or X-ray falls on a particle, it gets scattered in all possible directions. But because of the presence of certain planes in the crystal, when X-ray falls on the crystal, the scattered ray, they themselves reinforce each other to align in one particular direction. Now comes, what is the technique and what is the principle behind this? And how we can choose whether we will go for powder XRD or single crystal XRD. Now the principle is for both powder and single crystal XRD is the Bragg's rule. From the beginning we are studying, from in graduation or PG we had studied n lambda is equal to 2d sine theta, where n is the any integral number, lambda is the wavelength, d is the distance between the two planes, and theta is the angle between the incident ray and the plane. So if they satisfy n lambda is equal to 2d sine theta, only then it will diffract. And how we will choose? There, if we see the matter or material, there are two types of matter. It could be amorphous or crystalline. If our sample is of amorphous nature, we will go for powder XRD. If the sample is of crystalline nature, we'll go for single crystal XRD. Then in both powder XRD as well in single crystal XRD, what happened? What is when the Bragg's rule can be satisfied? A Bragg condition is such that the scattered ray from two parallel planes interact with each other in such a way to create a constructive interference. It's very important. They must satisfy the Bragg's rule, and along with that, a Bragg in what is there in the Bragg condition? The scattered ray. You can see here. This is the scattered ray. This is again the scattered ray, and the two scattered ray from two planes interact with each other in such a way to create a constructive interference. There be no interference. There are two types of interference, constructive interference and destructive interference. In constructive interference, the waves are in phase. However, in destructive interference, the two waves are out of phase. So here in the Bragg's condition, the two scattered rays from two different planes must create a constructive interference. Only then they can diffract. Now, what is the basic schematic presentation of the X-ray setup? If we talk about for the powder as well as single crystal, the basic components are the same. There's a high voltage stabilizer and X-ray tube through which X-ray is generated. Then it passed through a monochromator to extract one particular wavelength. Then the monochromatic X-ray has to pass through a collimator. With the purpose of the collimator is to align the X-ray or make them fall on the sample. Then excuse me. Sorry. Then after there, The detector will collect the diffraction and data, and through scaler, timer, and recorder, and through the printer, we get the final data. Now, this is the machine of single crystal X-ray. This is the single crystal X-ray diffractometer, the full machine. We use Bruker Advanced D8 XRD. Here's the chiller. Now, if we see, enlarge it, see, this is the X-ray tube. We can see this is the X-ray tube in which the X-ray is generated. This is goniometer. This is called goniometer, on which the crystal is mounted, and it rotates at several angles, and so that detector collects the data from different angles. This is the crystal loop in which the crystal has been mounted. This is the detector. We can see this is the detector. It also rotates along with that of the goniometer to collect data from each and every angle. This is the camera which records all the data. And here is the water jacket. Here is the water jacket in which there is a continuous supply of water to reduce the temperature of the target material. All the components are the same. X-ray tube with the target material. Here in single crystal XRD, we use molybdenum as a target material, whereas in powder XRD, generally we use copper as a target material. There's a voltage stabilizer, collimeter, monochromator, and then comes detector. Detector is very important, and the detector are based on two phenomena: excitation and ionization. Mostly nowadays we are using solid state detector. In our machine, that is a charge coupled detector, which is based on the same principle where the solid state detector works. Now come, like, we know that we have to characterize our molecule, and for that we need to grow a suitable crystal. So this is the first and foremost important step to for the analyzing your substance. For that, we have to grow a suitable, genuine single crystal of appropriate size and shape. And this is the first and foremost important step. We can grow the crystal through various methods. There are various methods through we can grow the crystals. But here we are going to discuss three methods, like evaporation method, diffusion method, and slow cooling method. So how we can grow our crystal through evaporation? We have to take our compound, and then we have to dissolve that compound in a minimum amount of solvent. I'm telling you that a minimum amount of solvent, because we have to make that solution as a saturated solution. Then we have to heat the solution to make it more and more clear, and then we will filter that clear solution to a test tube. Then we seal the mouth of the test tube with a paraffin and prick the paraffin with the help of some needle or something. Why we are doing the sealing and then pricking? Because we want to control the rate of the reaction. If we are not able to control the rate of the reaction, we will not get a suitable crystal, because we are not, otherwise we cannot control the size and the shape of the crystal. Therefore, in this process, it is very necessary to control the rate of the evaporation. What happened if we were not able to control the rate of reaction? Then we will end up with that kind of crude crystalline material. Although it is not bad if we get this type of crude crystalline material, this is also good. That means we are getting pure compounds. But again, what we have to do, we have to took some sample from some analyte from here. dissolve in a solvent, a suitable solvent. And now again, we have to be very cautious and very careful. That means we have to control the rate of reaction. Otherwise, we will not get single suitable crystals. Then comes diffusion method. Diffusion method is also known as layering method. In this method, we have to make two layers. Like we have to choose two solvent which is immiscible to each other. Mostly we dissolve our compound in the polar solvent, or most of the compounds are soluble in the polar compounds. So what we do, we take our sample, dissolve in the suitable particular solvent, and then we placed in this type of, you can see, can you see this tube? So this tube is crystallization tube. So what we do, we pour the clear transparent solution of our compound here in this tube, and then with the help of the wall of this tube, we add drop by drop the non-polar solvent or the solvent which is immiscible to that of the previous solvent. Then we have to seal the tube with the help of paraffin, prick it to control the rate of the reaction. Here we can see this is the this is the solution of our compound, and here is the transparent solution, the transparent solvent is which is immiscible with that of the previous one. The tube which I had shown you is a crystallization tube. It's similar to that of the NMR tube, but I would suggest do not use your NMR tube. That NMR tube is made up of quartz. However, this tube is made of borosilicate or something. So this is not expensive. Those NMR tubes are very expensive. Don't use that NMR tube for crystallization purpose. Otherwise, your supervisors will kick you off from the lab. Then comes slow cooling. The third one is the slow cooling, through which we can also get suitable crystals. In this, what we do, we take our compound, make a clear solution with a suitable solvent, and then we have to seal that tube completely. Here we have to seal the tube completely, and we keep that tube in the fridge. First, we have to keep that tube in the fridge where the temperature is around 4 to 6 degrees centigrade. Then after 10 or 15 days, if we are getting crystal, it's well and good. Otherwise, we have to transfer that tube from the fridge to the fridger, where the temperature is around 0 degrees centigrade. Now, again, if we get the crystal over there after a few days, then it's well and good. Otherwise, we have to shift the tube from the freezer to the deep freezer, where the temperature is -20 to -40 degree. That is called slow cooling. That means gradually we are cooling our solution. In this mostly we use acetonitrile solution solvent, and this is a time-taking process, and the probability of getting crystal here with the slow cooling process is very less. But once we get a crystal from here, it is a very good, small, well-ordered crystals. So these are the methods how we can grow the crystal. But the main important thing is that, like, there should be minimum mechanical disturbance during the crystallization. We have to keep in our mind, like, we should not disturb the crystallization tube or the tubes which are used for the crystallization purpose. There means there should be minimum mechanical distance or less mechanical disturbance. उसमें we should not disturb those crystallization tubes again and again. Now come how to pick a crystal and mount on the instrument. So this is the crystal loop head. The whole setup is called crystal loop head. At the top, there is a crystal loop which is made up of a transparent material. What we do then? We take a glass slide, uh, add a few drops of paraffin glue. Paraffin glue is nothing, it's just like glycerin, it's a transparent liquid, just like a glycerin. Then, with the help of a brush, we take out crystals from the tubes and make them float in the paraffin glue. Then, with the help of this crystal loop, we took out the crystal, and here we can see this is the loop, and here the crystal is there. The purpose of paraffin glue is that when we took out the crystal from the solution, it gets clumped with each other, and it would be difficult for us to get a single crystal. So what we do, we make them float in the paraffin glue, and then with the help of this loop, we pick one single crystal. All this is, we cannot see the single crystal through our naked eye, and it would be very difficult. So we use microscope. Nowadays, we have more advanced microscope that we can take the pictures, or we can click the pictures of our crystal. Then comes selection of an approach. We do the crystallization, we pick up the crystal, but whether the crystal is genuine single crystal, and we can either go for data collection. So for that we have to confirm ourselves. How we can do? We took our crystal and rotate through 360-degree. And during this, the field of view should go 2 times dark. Whenever that, if the crystal is genuine single crystal, what will happen if we rotate through 360-degree, then the field of view will go 2 times dark. Then again, the size is very important. The crystal which we are choosing for data collection, that should not be very small and should not be very large. It should be the size of the crystal should be moderate. If that would be large in size, the crystal will be in large in size, then what will happen? It would start absorbing the scattered ray, and this is not a good sign. So we have to choose a crystal of an appropriate size. Then in the crystal, there are 3 axes, A, B, and C. So the axis of rotation should be parallel to any of the axes A, B, and C, and the X-ray should fall perpendicular. Here is the axis of rotation, and the X-ray should fall perpendicular to the axis of rotation. This is the axis of rotation, and X-ray should fall perpendicular to the axis of rotation. Now, mounting of the crystal. How we can mount our crystal? We take the crystal in a loop. Now we have to place that crystal to the instrument. So we place that crystal loop on the goniometer, and before placing that goniometer, we have to be very careful that the crystal should be mounted at the crosswire of the camera and the detector. Here is the crystal in a loop, and this is the crosswire. So the crystal should be mounted on the crosswire of the detector and camera. Let me show you here. Here is the camera. You can see this is the camera and this is the detector. Before that, we have a computer screen. On that computer screen, we can see that cross wire. So the crystal, this is the goniometer on which we have to place the crystal loop, having the crystal. So the crystal has to be placed. The crystal has to be placed where where there is a crosswire of camera as well as detector. Now, diffraction pattern. No, sorry. We have mounted our crystal at the crosswire, and and how we can align the crystal by rotating it through 90-degree or 180-degree. We can align the crystal, and in the drive position, the crystal takes a center position, and in that drive condition, the detector also come close to the crystal. Then what is diffraction pattern? We mounted our crystal on the goniometer in the instrument, and then X-ray falls on the crystal. And as a result, we get a diffraction pattern. As a result, we get a diffraction pattern. In that diffraction pattern, we see number of spots. These spots will tell whether our crystal is single crystal, or we should go for data collection, or we have to stop at this position. So if we see a moderate number of spots with appropriate intensity, this means that the crystal is good. That means there's the number of the spots should not less, should not more, and moderate number should be there, or moderate number of spots should be there, and those spots have appropriate intensity. Along with that, these spots should not overlap with each other. They do not, it is like these spots should not overlap on each other, otherwise it will suggest like there is an overlapping of the electron density. Excuse me. There is a overlapping of electron density. Now we have collected we can see the diffraction pattern, and now we have to give the command to the instrument. So before going to instrument for giving the command, we should know what kind of crystal system we are having. As we know, there are different type of crystal systems. So we know there are 7 type of crystal system: cubic, orthorhombic, tetragonal, monoclinic, triclinic, hexagonal, rhombohedral or trigonal. So among the 7 crystal system, the cubic is the most symmetric crystal system. Cubic is the most symmetric crystal system where all the cell dimension A, B, and C are equal, whereas the crystal angles alpha, beta, and gamma are the same. Whereas the triclinic is the most asymmetric crystal system where all the cell dimension A, B, and C are not equal, whereas alpha, beta, and gamma, they are also not equal. So among the crystal system, cubic is the most symmetric and triclinic is the most asymmetric crystal system. So if we find in the unit cell parameter that there is triclinic crystal system, then we have to give command to the machine for 8 hours data collection. See, here we have to give 6 to 8 hours to the machine for data collection. So it's a very expensive and time-taking process. So for triclinic crystal system, we have to give 6 hours duration to the instrument for data collection, and for rest of the crystal system, 6 hours is good enough for the data collection. Now come, we have crystals, we go for data collection, we get the raw data. And then with the help of Apex software, we process the raw data. And finally, we get the REST file. REST file is nothing, it's a result file of that raw data. Then we are eagerly waiting for what is there in our molecule or what is there in our crystal. We just want to see. So for that structure solution, we generally use two type of software. That is, first is WinGX and the second is Excel. Excel is like more user friendly and now it is widely used. Therefore, I'm going to demonstrate here the Excel, how we can use Excel for a structure solution. Now you have to open, I'm going to demonstrate through the software also. So see, we will first open our program, then we'll go in the file menu, upload our file, and then what we see here, we see all the Q peaks. There are Q peaks. Those Q peaks are nothing, but they are electron density. And depending upon like what we have some idea like what kind of reaction we did and what we are expecting in our product, we will assign those Q peaks as carbon, nitrogen, oxygen, whatever atom we want. What happened? If we open the REST file, we'll see certain Q peaks. Those Q peaks are the electron density. Those Q peaks are the electron density. And now we have to assign those Q peaks or electron density with our desired atom. And we will label them, then refine them, and add hydrogen on those atoms. Then ultimately we create the CIF file. CIF file is nothing, it's the crystallographic information file. The CIF file is having all the information, bond length, bond angle, then A, B, and C parameter, alpha, beta, and gamma. Z. Z is not is Z. What is Z? Z is the number of molecules present in one unit cell. Then during refinement, we can see there are three values, R1 and R2. These are called refinement parameter. This R1 and R2 are the refinement parameter, and this suggests the reliability, how much we can reliable on our data, how much we can trust on our data. The R1 should be less than 10 and the WR2 should be less than 20. So here we are getting 0.04 and 0.12. That means we are getting very good data. Okay, so this is goof value. This is goof value. Goof value is the goodness of fitness. This also suggests that we can rely on our data. Now I will demonstrate you.
Sorry to interrupt you, ma'am. Sorry to interrupt you. Will you please do the setting in that annotation set? Enable participant to do the annotation. Please close it so that participant cannot annotate the screen.
Is it okay now?
Yeah, in annotate share a screen where you will be getting up top side. You are getting an option.
Yeah, annotate.
So enable the participant to do the screen annotation. If this is check one, then uncheck it, please.
I had clicked on the annotate. Then what to
do?
No,
No, you're not supposed to don't let them annotate the screen.
Just wait a minute, ma'am.
Yeah. Participant, please do not annotate the screen. We are expecting a cooperation from your side. Thank you.
I'm not able to do that, ma'am. There is an icon, a note, then
It's okay, ma'am. You go ahead. If there's anything like that, I will make the necessary correction. Go ahead, ma'am.
Yes,
No problem.
Okay. Thank you, Kyle. Thank you, ma'am.
it's okay. So shall I continue?
Yes, ma'am, you can.
Okay. Are you able to see my screen? Now I'm going to demonstrate how to use the software.
Yes, yes.
Okay. So we will open our Excel program and then we'll go in the File tab, load our program. Here is the res file, that is a result file which we get from the raw data. Open your file here. Now we can see these are the Q peaks. These Q peaks I had already told you that these are electron density and we have to assign them with certain atom, what we are expecting in our molecule. So reduce the number of Q peaks. Here is our structure. Now suppose we want to change it. Then in that case, we label it C4 again, and then we have to go for refinement, refine it. See, after refinement, we see these parameters R1 and WR2. This will give an idea like how much we can rely on our data. This
Excuse
means
me, ma'am.
yeah,
Ma'am,
sure.
nothing is there on screen, like it's frozen. It's saying no coordinates available. Only we can see the file Mercury and the Diamond software, but
Oh,
nothing is more than that.
just wait a minute, ma'am. Now you can see.
No change, ma'am.
Now you would be able to see. Are you able to see now?
No, ma'am. It's showing right now types of models, hydrogen bonding and packing in the 3D space. Either you stop sharing and restart the sharing, I guess it may help.
And definitely I will do that. Now you are able to see, ma'am?
No, ma'am. You need to stop sharing and restart the sharing, ma'am.
I'm doing that, but it's not coming actually.
Now restart the screen, ma'am. Sharing the screen again.
Now you can see the Excel program?
No.
No.
You need to share the screen again.
Now you would be able to see, I think.
Yes, now we can. Yes,
Okay.
yes. Thank you, ma'am.
Please let me know if you are not able to see.
Yes, yes, ma'am.
So here's the molecule. I will show you from the beginning. Like from the load file, you have to load your res file. Open your res file, and here we can see certain Q peaks. These Q peaks are the electron density, and depending upon like which what we are expecting, we have to assign them, whether it is carbon, nitrogen, or oxygen, and whatsoever atom is there in your system. Then we have to refine it. Here we are having R1 and WR2. These two factors are the refinement parameters. This R1 and R2 is known as the refinement parameters, and this will tell about the trust, like how much you can trust on your data. This is the goof value, this is the goodness of fitness, value. No. This is how we can do a structure solution. And now we know what is there in the crystal. What is what the ultimately product we are getting. We know all the information about the what is there in our crystal. Now, with the help of are you able to see my presentation now?
Yes, ma'am, we can.
Okay. So now we know what is there in our molecule, and now we are more expecting how the molecules are oriented in the three-dimensional space, what kind of interaction is there, what packing is there. So for that we use Mercury and Diamond software. These two softwares are very user friendly, and we can get these are not licensed software, so we can get from the website, and we can download it. That is free of cost and very useful and very good software. So first I will tell about Mercury software. In Mercury we can represent our molecule in 4 or 5 different ways. I will show you. Yeah. The same molecule here, we can show our molecule in 4 or 5 different, there are 4 or 5 different models through which we can depict our molecule. This is called a space fill molecule, space fill model. Here, this is the ball and stick model. And what is there? Ball. The atom is depicted as a ball and the bonds are depicted as a stick. So it is known as ball and stick model.
Excuse me, ma'am. Again, it's got frozen. It's not showing the what you are saying.
Oh my God. Just wait a minute, ma'am, then. Can you see my presentation now?
No, ma'am. It's there as it is. It's not moving. Or might be the file is very huge, so you have to again stop sharing and reshare your screen.
Let me do that.
Now we can see the different model which you are showing on the screen.
Okay, thank you. So with the help of Mercury software, we can see our molecule in 4 or 5 different ways. This is the space fill model. The same molecule, we can see the space fill molecule. How it is, the electron density, that means there is a long range of electron density. In this model, we can depict. In the ball and stick model, the atoms are being depicted by balls and the bonds are depicted by the stick. This model is known as ball and stick model. Then this comes capped sticks, like all the atom as well as the bond is depicted in the form of sticks. And then wireframe model. The most the most important model is the ORTEP model. That is Oak Ridge Thermal Ellipsoid Plot. This mostly, if we write a paper, then most of the reviewer want your structure in this ORTEP model, because if there is any error in your structure, the structure itself shows how much error is there in your structure. So we were talking about the Mercury. The first and the foremost important thing in Mercury, like we can show our molecule in 4 or 5 different ways. The second is that types of hydrogen bonding. We can show With the help of Mercury software, what kind of hydrogen bonding is there, how which atom is connected through which atom, and how they are arranged in the 3D space, what kind of packing is there in the three-dimensional space. Then the next thing is that insertion of dummy atom. We can also, like, we have a phenyl ring. Suppose we have a phenyl ring and we want to generate a electron density, pi electron density. That means we have to create a dummy atom at the center of the phenyl ring, which will act as a pi electron density for making a CH pi interaction or pi pi kind of interaction. With the help of Mercury software, we can also do powder XRD pattern. I will also demonstrate these two with the help of Mercury software. For example, I have taken a simplest example, like we are having one pyrazole. This is diphenyl pyrazole. 3,5-diphenylpyrazole. When it reacts with the phosphoric acid, one of the proton get transferred to the lone pair of this nitrogen and it gets protonated, and in the vicinity the dihydrogen phosphate is present. Simple. We take your compound, add methanol, add phosphoric acid, and do the reaction, and we will end up with a beautiful crystal. Then we did the data collection and we found this type of data. This is the structure I had drawn with the help of Diamond software, and these are the structure refinement parameter which I had taken from the CIF file. As I have already told you that CIF is the file, crystallographic information file, and that file compiles all the information, and we will get each and every information from there. We can get the empirical formula, formula weight, crystal system, type of space group. I will show you each and everything. Just wait. How we can write and how we can make a table for structure refinement parameter. Then comes non-covalent interaction. So what is non-covalent interaction or hydrogen bonding? If for hydrogen bonding, if the hydrogen is attached to certain atom and it in the vicinity there is some atom with certain electron density, then there is a bonding, now weak bonding between the hydrogen and the acceptor atom, and that is called hydrogen bonding or short contacts. So for short contacts, how we can draw short contacts, and for that we need four things: the distance between donor and hydrogen, the distance between hydrogen and acceptor, the distance between donor and acceptor, and the angle of donor, hydrogen, and acceptor. So what is the distance of D and H? So D and H, this is the donor atom with which the hydrogen is attached. So this distance is known as donor hydrogen distance. Then hydrogen and acceptor. Suppose this is the acceptor, electron density. I had already told you this. Suppose we have to make a pi electron density. So we have to insert an atom over here. And then the distance of this CH through this, so the distance of this H to this acceptor is 3.216. So that is H and A distance. Then D and A. So we have to draw this a distance between this donor atom and then this acceptor atom. Then we calculate this distance. This is the distance of donor and acceptor atom. And then comes the angle of donor, hydrogen, and acceptor. This is the donor, this is the hydrogen, and this is the acceptor. So the angle, this will be angle DHA. These are the four important things what we have to note for making a short contact table. Now, with the help of Mercury software, we can generate a powder XRD pattern for a single crystal also. This is the simulated powder XRD pattern. And from our sample, we get this powder XRD pattern experimentally. And when we compare these two, the simulated one and the experimental one, then we can say about the structural homogeneity of our bulk sample. The bulk sample, we can say like the homogeneity is same. There is a homogeneous compound is there in our system when we compare the experimental data of powder XRD with that of the powder XRD, which is generated or simulated through the Mercury software. This is an example of Mercury software. Then comes Diamond software. How we can use Diamond software? We can use Diamond software. We have to open our file. Here also we have to open the CIF file, and with the help of there are certain programs. Then with the help of that program, we can grow our molecules, define their 3D dimension, how the molecules are arranged. Here I had shown you, in the previous slide I had shown you, like this is the crystal structure where the dihydrogen phosphate is there with the protonated pyrazole. If we grow only this, then in the crystal system, it had been found the two dihydrogen phosphate forms a dimer. These two dihydrogen phosphate forms a dimer. See, here is the donor atom through which hydrogen is attached. Here is the oxygen atom which act as a acceptor, and here it forms donor hydrogen and acceptor. Similarly, the oxygen bearing this hydrogen, now it will act as a donor. Hydrogen is attached to the donor, and this is acceptor, and now it is a donor hydrogen and acceptor. So the dihydrogen phosphate self dimerize in this way. This is the way how to write the thing or dimer in the supramolecular chemistry. I will show you. This forms a ring. This forms a ring. Therefore, R is used. Number of donor atom 1 and 2. 1 and 2. So we had written number of donor atoms, number of acceptor atoms. How many acceptors are there? 1 and 2. So 2, and total number of atoms involved in forming the ring. 1, 2, 3, 4, 5, 6, 7, and 8. So ring is there, number of donor atom is there, number of acceptor atom is there, and total number of atom which is being involved in forming that ring. This is the way how we can write in supramolecular chemistry. Before that, I would like to share Are you able to see my screen?
Yes, ma'am, we can see, but it is not in the PowerPoint presentation mode. We can see all the like slides mode.
Now I'm going to show you how to use Mercury.
No, the previous screen is, I guess, is on this, is shared. Ma'am, again, stop sharing and reshare what the next screen you want to show.
Sorry for the inconvenience.
It's okay, ma'am.
Now you can see?
No, ma'am. You need to share the screen.
I had already. Can you see now?
No, ma'am. Now we can.
Okay. Okay, so I'm going to demonstrate how we can use Mercury software for our system or molecule. First, we will open the CIF file. This is the CIF file. See, this is the diphenyl protonitrile, and in the vicinity, we can see the dihydrogen phosphate molecule. Are you able to see now?
Yes, ma'am, we can.
Okay, then that's great. Now we will go and see, as I had already told you, there are 4 or 5 types of way in which we can see our molecule. So we'll go in display in a style. This is the wireframe model. Then comes ball and stick model. Here, can you see this? Ball and stick model. This is the atoms are in the form of ball and the bonds are in the form of sticks. This model is known as ball and stick model. Then we'll go and see the ellipsoid model. Ellipsoid model is there. Then, excuse me. Then comes space fill model. Here is the space fill model, which gives a complete electron density of the around the molecules. This is the space fill model. Here we give the complete electron density around the atom. So these are the way to see the molecules. These are the different models through which we can depict our molecule. Then comes what is the how the molecules are interconnected. Then we'll go for hydrogen bond. We'll select it, extend these hydrogen bondings and see how this is formed. Suppose then we have to delete this hanging contacts. See, zoom it out. I can show you in a ballistic model. See, this is the oxygen, hydrogen, and oxygen, and there is also donor hydrogen and acceptor, donor hydrogen and acceptor. Here we can see the dimer of dihydrogen phosphate. This is the oxygen, hydrogen and acceptor, oxygen, hydrogen and acceptor. These are the this is the dimer of the dihydrogen phosphate. Then comes how we can insert a dummy atom in that. For that, we have to select all the 6 benzene or phenyl ring atom, carbon atom. Then we'll go into the centroid. Centroid, this will create a centroid atom. This means the pi electron density. There is this is called the pi electron density, and through which we can do a modeling. We can calculate the distance. We can also measure the distance by selecting the particular atoms. I had selected this carbon, this hydrogen, and the electron density of this phenyl ring. Then we can also calculate, we can see the 3D packing. Here, 3D packing, I had selected 3 into 3 into 3, that means three set of, in x-axis, y-axis, and in z-axis, three set of molecule. So along c-axis, we can see this type of arrangement where the four protonated diphenylpyrazoles are arranged in such a way to form a cavity, and within the cavity, these two molecules are being trapped. So through this software, through this Mercury software, we are able to identify how the molecule is arranged um, in the 3D space, what kind of interaction is there, how they are uh, uh, interacted with the other molecules present in their vicinity. So all these information we get through this Mercury software. Now we can also see the powder XRD pattern. We can generate or simulate. We get this simulated XRD powder pattern, and then we had collected the powder pattern for our sample through experimentally. And then with the comparison of these two, experimental as well as the simulated one, then we can check the homogeneity of our bulk sample. So these are the applications of this software. And one more thing I want to show you. Then when you open this CIF in a notepad, are you able to see this notepad?
No, ma'am. Only the previous screen where the XRD patterns are shown.
Okay. I think you are able to see this notepad.
Yes, ma'am, we can.
Okay. So here is the crystallographic information file. We have to open this file in a notepad, and this will give all the details how we can make a crystallographic or a structure refinement parameter table. Here we can see the chemical formula or the some chemical formula. Here's the total weight. So then the cell type, like what is the crystal system, orthorhombic, the space group, the alpha, beta, and gamma, the A, B, C, the other cell dimensions, Z. Z is the number of unit cells, number of molecules present in the unit cell, reflections, theta, the theta minimum, and this is the theta minimum and theta maximum, color, size, absorption coefficient, everything we can get from this CIF file. And at the last, we can see the refinement parameters, that is 3 and 10. That means the refinement parameters group value we can also get from this file. Now I would like to tell you how it is very important. The XRD is very important in seeing what is there in your molecule and how it is arranged. So I had taken the simplest example, the diphenylpyrazole. When it reacts with any acid, suppose phosphoric acid, nitric acid, hydrochloric, sulfuric, or perchloric acid, then in every case, what happens? The hydrogen get transferred to one of the nitrogen bearing the lone pair of electron, and the counter anion is present in its vicinity. So we can see here the different system get crystallizes in different crystal system, orthorhombic, monoclinic, that means the same ligand in presence of different anions get crystallizes in different crystal system and is having different kind of orientation or 3D orientation, and different type of short contacts or hydrogen bonding is there. I will show you. This is the first case. As I had already told you, these are the protonated pyrazole ring and capturing the dimer of the dihydrogen phosphate. And if we see the 3D packing, like without dihydrogen phosphate and with dihydrogen phosphate, these are the cavity which is filled by this. The pyrazoles are arranged themselves in such a way to make a cavity for the dihydrogen phosphate anion. Now, similarly for nitrate ion, in case along with the nitrate ion, 1 mole of crystalline water also crystallizes here. And and similar to the previous case, here also the 4 molecules are engaged in such a way to make a cavity for trapping the nitrate as well as water molecule. Here is the 3D packing without the guest molecule and with the guest molecule. Now, if we see the chloride, if we see the reaction of this pyrazole with the hydrochloric acid, then in that case, we get this kind of structure. And here, the pyrazole rings are not able to make a cavity. Why it is so? Because the distance between the two pyrazole, now the electron density, the CH pi interaction is ranges in around 12 Armstrong, which is quite good, large. It's very large to make a true cavity. That means the CH pi distance in this case is found in the range of 12 Armstrong, which seems to be very large to for the formation of a true cavity. So in this case, we didn't get any cavity. In previous two cases, we get the cavity in which the dihydrogen phosphate ion, the nitrate ion is present. But here, the pyrazoles are not able to make a cavity. In case of sulfuric acid, what the unit cell or the asymmetric unit consists of 8 molecules of protonated pyrazole, 4 molecules of hydrogen sulfate, 2 molecules of sulfate ions, along with that 3 mole of crystalline water. Here also, the pattern gets entirely changed. Here, the protonated pyrazoles, see the protonated pyrazoles make a channel in which the sulfate, the bisulfate, as well as the water molecules are arranging. These are the two parallel chains of the protonated pyrazole in which these molecules are sitting. Similarly, in case of perchlorate ion, along with the perchlorate ion, 1 mole of crystalline water and 1 mole of methanol is also crystallizes. And here we also get the same kind what we have in the sulfuric acid. In the case of sulfuric acid, here also the protonated pyrazole make channels, see, and then the water molecule, the perchlorate and the methanol molecules are present in or trapped in between the channel. So we can conclude that variation of anion or variation of anything present in the vicinity has a controlling effect on further structure, or is a significant role, plays a significant role in controlling the structure. And why this control? Because it ultimately controls the number and the type of interaction and the orientation of the molecule in the 3D space. With another example, I would like to share, like when copper chloride reacts with pyrazole, 3,5 substituted pyrazoles. Firstly, we had taken diisopropyl 3,5-diisopropyl pyrazole. In second, 3 tertiary butyl 5-isopropyl pyrazole, then 3-methyl 5-phenyl, and 3 cuminyl and 5-methyl pyrazole. We have 4 set of pyrazole. And when this substituted pyrazole reacts with copper chloride, in each and every case, we get dichloro-bridged dinuclear copper complex in every complex, in each and every case. But the thing is that because of the difference at R1 and R2 position, like the substitution are at 3 and 5 position are different, so we get there is a difference in the bond length and bond angle, as well as there is a difference in between the two copper centers. The distance between the two copper center also varies. I had already highlighted it. And it has been noticed that in each of these cases, we get one-dimensional ladder-like packing in all the 4 complex, but their packing is entirely different. Here we have, or in all the 4 cases, we get the one-dimensional chain-like packing, but all the 4 packing are different from each other. Therefore, we can say the steric hindrance or the substitution present on the 3,5 position of the ligand controls the geometry of the complex and hence the reactivity too. We did some reactivity tests of, and then we find that the substitution present over there controls the orientation of the molecule and ultimately the reactivity too. Then comes powder XRD. What is powder XRD? When the crystallite size is very small, um, like we are not able to go for single crystal X-ray diffraction, then we can use powder XRD for knowing more about our analyte or for more about our sample. So powder XRD provides information about the crystalline structure. In a sample, even the crystallite size is too small for single crystal X-ray diffraction. The method is same as we had already discussed in the single crystal. Here, X-ray is being produced by hitting the target material. X-ray is produced, and then this X-ray through monochromator and collimator falls on our sample or analyte and gives this type of pattern. Here the thing is that in single crystal XRD, we get this kind of X-ray pattern where we have spots, moderate number of spots with appropriate intensity. But in case of powder XRD, we didn't get any spots. Why it is so? In crystals, we have certain planes. We have planes, and because of the planes, we get this kind of spots. But since in powder XRD, the planes are in random way, there is also plane, but those planes are not in a those planes are not arranged in a proper way. So that is why we do not get any spots in the diffraction pattern of powder sample. This is the machine we use for powder XRD. Then comes what we get in the single crystal, we get the raw data. Here in powder XRD, we get a powder XRD spectra in which the exact there is 2 theta on x-axis. Mostly the theta ranges from 5 or 10 degree to 70 degree, and then there on the x-axis we have intensities or counts. Here also the incident beam will be scattered at all scattering centers which lay on the lattice plane. The beam scattered at different lattice plane must be scattered coherent. The angle between the incident and the plane is theta, whereas the angle between the incident and the scattered ray are 2 theta. The angle 2 theta of maximum intensity is called the Bragg angle. What are the applications of XRD? There are various applications of XRD. First is the crystal structure determination, precise lattice parameter measurements, identification of known specimen, unknown specimen, how we can use this powder XRD for knowing our sample. We have our XRD patterns, and there is a library in which various compounds, there is a powder XRD of various compounds. We have to compare these two patterns, and after comparing, we can know about like which component is present in our sample. Similarly, quantitative analysis of powder mixture we can do with the help of XRD. Determination of crystal size and lattice strains we can do. Phase diagram determination, detection of long range ordering, evaluation of texture in polycrystalline solid. So determination of crystal size we can do also with the help of D by Scherer formula in powder XRD. So what is the D by Scherer formula? D by Scherer formula is nothing. It's the thickness is equal to 0.9 lambda divided by under root of bm square minus bs square and cos theta, where lambda is the wavelength, theta is the Bragg angle, T is the crystallite thickness, which we have to calculate, and BM and BS is the full width at half maximum of your sample as well as the reference material. So what is full width at half maximum and how we can calculate? If we see this is the P and we make a line, we make a vertical line up to the tip of this peak, and then we calculate the length of this line, just half it, make divided by 2, make it 2 divided by 2 half, and then on that point make a horizontal line between these to measure the distance between these 2 points. This length is known as full width at half maximum, and through which we are able to calculate the thickness of our sample. So at the end, I would like to thank you, all of you, the organizer, the participants. And at the end, I would like to say, like in real life also, we should get crystal of joy. And how we can get the crystal of joy? So in that case, you have to evaporate your tears, just like we are evaporating our solvents, and precipitate your sorrows. Only then we will get the crystal of joy. Thank you.
Thank you so much, ma'am, for this wonderful session with good demonstrations. I would like to address 2 questions from the audience, ma'am.
Yeah, sure, ma'am.
So the first question would be, how much R factor is good enough for a good crystal?
Okay.
How much R factor is good enough?
Yeah. So here I had written, this is In terms, I had talked in terms of percentage, but here it is 0.03. Are you able to see? This is R1 and
Yes.
WR2. Are you able to see, sir?
Yes, yes.
Yes. So R1 and R2, if the R1 is supposed to less than 10 and WR2 is supposed to less than 20, in that case, your data is good. That means the minimum amount of the minimum number of R1 and R2 will show you like more reliability on your data. You can trust on more trust on your data. So lesser is the value of R1 and R2, more reliable is your data.
The second question that has come from the audience, ma'am, is on what factors do the XRD spectra of ionic solutions depend? What factors?
Can you repeat it again, sir?
On what factors do the XRD spectra of ionic solutions depend?
So ionic solution, as such, we cannot use ionic solution, sir. We have to get a crystal. Only then we can go for XRD, single crystal XRD. Unless until we don't have single crystal, we cannot go for XRD, because on the loop, you cannot put your solution over there.
Correct. So thank you so much, ma'am.
Okay.
There will be more questions from the audience, but we will only be taking a few in. So we would request you, ma'am, if we could share your email ID with the students. Would that be fine?
Yeah, I had already given you,
Yes.
like in
So
the
they
last
could put the
slide.
questions to you.
In the last slide.
So audience, please make a note of ma'am's email ID so that you could contact ma'am for your doubts and further questioning in relation to the topic.
Is it there? sujata.iitr@gmail.com?
Yes, yes.
Okay.
Yeah. Just keep that presentation on so they can note down the email ID. Thank you so much, ma'am.
Thank you very much, sir.
Till then, I would like to invite Maria Gomes from our department faculty members to address the audience and offer our gratitude to you, ma'am. Over to you, Maria.
Thank you, sir. Am I audible?
Yeah.
Yes.
Good morning, everyone. That was truly a gripping session. I appreciate Dr. Sujata for the brilliant presentation and thorough coverage of the topic. It has inspired us to have a passion as that of yours. Starting from the basics, the do's and the don'ts, the applications, and the oh so easy demonstration of the topic, of the software, and for clearing our doubts. Thank you, ma'am, for making this complex instrument so simple and easy for us to understand.
Thank you very much. Thank
I,
you.
Maria Gomes, on behalf of the Department of Chemistry, St. Xavier's College, and all the participants, would like to express our gratitude to you for sharing with us your insights and valuable time. We are privileged to have benefited from your knowledge. Thank you, ma'am.
Thank you. Thank you very much.
So thank you so much, everyone. And for all the participants, I am putting out a poll. Please answer the poll. After this, you can have a 15-minute break. We will come back for the next session. Thank you so much. Thank you so much, Sujata ma'am. Over to you, Abhilasha ma'am.
Yeah.
Thank you. Thank you,
Thank
sir.
you, ma'am. Thank you, ma'am. Thank you for your wonderful presentation. Participant, please answer the poll question, and then we'll break for 15 minutes and join the session for the next GCMS techniques. Thank you very much.